Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Thank you for joining us. We're very happy to have Stefanie Mueller here today, coming from the Hasso Plattner Institute in Germany. She is widely recognized as one of the leaders in personal fabrication, questioning the notion that 3D printing and things like this are fast, and instead looking at how slow they are and how inexpressive they are, and the challenges that we're going to encounter in making these part of the future of everyday interaction. Multiple award-winning papers for her work, a regular face now on the top conferences in the field, so really a leader in the space. Very exciting to have her here today. So let's welcome her. Thanks.
Yeah, thank you very much for the introduction. So I'm very excited to talk to you today about my research in interacting with personal fabrication machines. So the underlying vision of my research is that I believe that in the future, everybody will be able to create complex physical objects that only trained experts can create today. So when I say objects, I mean both. I mean objects where shape is the most important aspect, such as decorative objects, but also functional mechanical devices. So on the hardware side, 3D printers have already started to enable this vision. So instead of having a specialized mechanical tool for every engineering task, 3D printers provide this generic platform that can be operated by anybody. However, it's currently really unclear what interaction model these 3D printers should provide. So here you can see the current interaction model. Users sit at a computer, they use a digital 3D editor to create a design, and only at the very end of their workflow, they send it to the 3D printer and create the physical version. And this is really a problem because many physical objects have to be tested in the physical world where they ultimately belong to. So for instance, when you create this pair of glasses here, it's not enough to have the digital version. You really have to test it on the head. Does it fit right? Is the pressure behind the ears correct? So the reason why we currently use this interaction model with the delayed feedback is because 3D printers are very slow. So if you print something the size of the glasses, easily takes a couple of hours. If you print something that's slightly larger, requires overnight printing. So this overnight printing, overnight processing, this interaction model probably sounds very familiar to many of you because we have seen this before somewhere else. So in the early days of computing, users also had to first generate an input, then send it to the machine, and in the next morning, they could see the result. In case they made a mistake, they had to wait another night, try again, until they finally succeeded. So as you can imagine, since the feedback is so much delayed in this interaction model, it's really limited to expert users, because you really have to know what you are doing in order to succeed at the end. However, in personal computing, we are today at a point where everybody can use a computer. So what did change in the interaction model? So first, when processing got faster, users could now work more in a turn-taking style interaction. So they could type something in the command line, get feedback. If they made a mistake, could try again quickly. And then second, when we moved from this expert command line tools towards more direct manipulation with the graphical user interface and natural user interaction, users could now work hands-on on the data instead of remembering all these expert commands. However, today's naive version of simply taking this 3D printer and adding it to this type of interaction does not work. Because by adding this 3D printer, we are back in batch processing mode. So you have overnight printing, physical feedback is delayed, and then also there's no way how you can work hands-on on the physical data here. You always have to go back to the digital 3D editor. So in my research, I asked myself the question, how would a system look like that reintroduces these interaction qualities? And I believe it would look like this. So users work hands-on on the physical data, and after editing step they make on the physical data, on the physical matter, they receive immediate physical change. And I call this interaction style interactive construction. So in the remainder of this talk, I want to show you how we can reintroduce these two interaction qualities, the fast feedback and the direct manipulation, to enable such an interactive construction system. So when I started my research, I started out with the general question, how can we actually make fabrication faster because it's currently so slow? And for this, I got again inspired by the history of computing. So when processing was slow, researchers suggested a method called low-fidelity rendering to give users an early preview. So I applied the concept to fabrication. So instead of always doing a full, slow, high-fidelity print, I suggest that we only spend printing time on the part that's currently being tested, and then the rest is replaced with a low-fidelity context material. So you can see this idea again. Intermediate versions, low fidelity. The final version is then high fidelity. So I developed a range of low fidelity techniques for different prototyping goals, and I'm going to walk you through 3 of them. And the first one was with a focus on modularity. So let's take this example of the head-mounted display body here. So I'm currently prototyping this. It's a virtual reality headset. You attach your phone, can experience some 3D stereography image. And the first thing I want to find out is if the lens distance to the display is right. So if the lens is out too close, image is blurry, too far away, the same thing. So in a normal process, you would spend more than 14 hours waiting for first version. However, here I decide to use our software. So I load the 3D model. And now with just a few clicks, I can convert this into a low fidelity representation. And now that I have this low fidelity representation, I can go in and say, but here, this part I want to have high fidelity. Here I want to spend my time on. So when I'm done selecting my part, I simply click the export button. I get the 3D printable file. You can see there's also an ID engraved. And now while this part is printing, I can already start assembling and just insert the part once it's ready from the 3D printing. And you can see there are on-screen instructions that tell me how to put the model together. So as I said, this is not a final version. It's an intermediate prototyping iteration version. And now you can have one where you can actually test the functionality in already 1 hour instead of waiting overnight to the next day. And as you can imagine, this modular approach allows you to then take off parts and test different versions. So for instance, for the forehead piece here, making it exactly the roundness of your head, nose piece, etc. So from the implementation side, there are several challenges. One is, for instance, how can you construct a constructible brick layout? So here you see a connectivity graph of the different bricks. And as you can see, for instance, here on the right side, this part would fall off and needs to be relayouted. Then also, when we generate the custom geometry for the bricks, we have to intersect bricks with the original model. And then sometimes things can happen, such as that a part of a knob, for instance, is cut off, which we then need to reconsider in our layout algorithm because this knob cannot be used to create a stable connection. So the project is now online. If you want to give it a try, you can find it under this domain there. So the Lego version I showed you was really great for modularity, but as you can imagine, especially when you have the head-mounted display on your head for a while, there are pull forces to the back. The bricks are very modular, but also fall apart after some time. So we developed a second fidelity technique, which takes a 3D model and converts it into a representation for laser cutting. So laser cutting of 2D plates. So you can see the same model I showed you before, but now it only takes 20 minutes to actually fabricate a first version. And with our software, you can also select different conversion types that you want. So for instance, here, you can see that the head part here is 3D printed, the rest is laser cut. So again, we provide a piece of software. You load your 3D model. And then you have one slider where you can drag from fidelity towards speed. And as you drag towards speed, we replace more and more parts with parts for laser cutting. So what is always really important for me from the user interaction side is that the user does not need to have any low-level domain knowledge. He simply clicks export button, gets the file, sends it to the device, gets assembly instructions, puts it all together. So to find the plates, we first group all neighboring faces with the same normal, and then we look for planes that have an opposite normal within a certain distance d. So the distance d here is the laser cut thickness of your acrylic plates that your cutter supports. In the end, our algorithm outputs a segmentation that looks like this. So here you can see, just for visualization purposes, different colors represent different plates here. And internally, this is represented as something that we call a plate joint graph. So this plate joint graph is an abstract data structure which shows the connectivity between different segments. And it's mainly used for calculating the different conversions as the user drags the fidelity slider. So at the beginning, you can see here, we are on high fidelity, so everything is labeled 3D print. But as we keep dragging towards speed, all these segments are then labeled laser cut. Each edge then represents a connection between the segments. So by default, this is just finger joints, so tabs that click together. But we also support something that's a one-dimensional bend. So if you, for instance, have a heat gun which allows you to bend acrylic, you can simply go into the software, say this here should be bent. And then when you export that file, our algorithm flattens it. You can then laser cut it and bend it into the final shape. So in case of the bending, we also use the plate graph, but this time we also have to check if all of these segments are laying on a one-dimensional curve. So to evaluate our technique, we downloaded more than 2,000 meshes from Thingiverse, which is a 3D model database, and we automatically piped them through our conversion algorithm. And we found that for more than 40% of the models, we save 10 times. We have a speed up factor of more than 10 times. So if you think about it, you can do 10 times more iterations in one day. Of course, on the other side, there are also some shapes which don't work well. So anything that has a curved shape, which is really hard to represent on a laser cutter. Which actually brings me to my third low-fidelity technique I want to show you, fulfilling kind of this matrix of different techniques, which is for shape objects. So here you can see this. Instead of printing a high-fidelity version with a solid surface, we suggest to print a wireframe. In this way, you save more than 90% of the printing time. The great thing here is, as you can see, the overall shape is preserved. So if you want to test something, for instance, like the ergonomics of this bottle in your hand, you can still test this with the low-fidelity version. So the reason why wireprint is actually so fast is because we generated the special printing technique here. So normally in 3D printing, you print layer-wise. So it's like one layer on the next layer on the next layer. But as you can see here, we also print in Z direction, so we also print upwards. And this is what makes it so fast. However, when we initially started, this wasn't clear to us. So our initial idea was, okay, if we save material, we are probably also going to save a lot of time. So we printed this cube here, layer-wise with solid walls, and the other one, a wireframe, also layer-wise. And what we found here is, wow, we save a lot of material, but actually the speed up is not that large. So it's like roughly 2 times faster. So the question was, why is that actually? And we found out that the printhead still has to go to each corner on each layer. So the printhead path remains almost the same no matter if you print a wireframe layer-wise or solid surface. So our second hypothesis here was now, okay, we probably have to optimize the printhead path to actually save a lot of time. So this cube now is printed going upwards, and now we actually save more than 90% of the printing time. Yeah, so as always with research, never works at the beginning. So what we learned from this is, so the material comes out, it's warm and it's liquid, and if you print upwards, you actually have to make it solidify really quickly. Otherwise, you get, for instance, these curves or some other squishy mesh. So we found 3 ways how you can support the solidification. So the first one is to choose the right printing material. So materials are not only liquid and solid, as we all know, but there's also a range where they are viscous in between. So the right material for us actually has a very small transition range from liquid to solid, so solidifies very quickly in the small range. So in our case here, ABS plastic worked the best. Then you can also add cooling hardware to your system. So we did an initial test by just putting the printer in a fridge. Worked great. And then we did a more professional setup. So first with 2 blowers on the side, blowing cool air on the print. A stronger setup with more cooling, had a compressor pumping air through this 3D printed air duct here. And then our final version now has water mist cooling with atomizing sprays, cooling the print very quickly. And then there's a third way how you can optimize the solidification. It's actually in software. So 2 ways. Either you print very slow as you go and you let the material solidify as you go. Or second way, you print very fast, but you pause at the critical feature points. So everywhere where you could get one of these potential deformations, you make a pause. So we ran an experiment where we varied printing speed and pausing. So on the bottom right, you see a slowest printing speed, 0 pause. And here you can see fast printing speed, but a 1-second pause at all the critical feature points. And we found that this works actually best. So it has the smallest printing time while still preserving overall print quality. So now that we know how we can actually print upwards, the question still remained, how can we convert a 3D model into a wireframe representation? So our initial idea was to just take the edges that we already have and go along them. But as you can see here, the print head causes certain collisions. So if you print too steep or too close to existing material, you're going to knock this down. Still, as you can see here, there are different conversions that fulfill these constraints of the print head. And I'm just going to explain the one here on the left to you. So the new edge pattern that we use always prints a contour, then a zigzag on top, and then another contour on top. And this allows us to convert any 3D mesh that has a surface representation into one of our wireframe patterns. Some features I want to point out is, for instance, we have different slicing heights. So on the ear, you can see the top parts are thinner sliced than the bottom parts. We support geometry splits in the middle, so the head of the bunny here splits into the 2 ears. Then all of the vertical lines are aligned for extra stability. And then also on each slice, we have a different number of feature points to represent the geometry. So when we start the slicing, we always start with the maximum slicing height, which is again determined by the printhead shape. So if you can make the printhead, for instance, thinner, you can also have larger slices. So first we slice at the maximum height, and then we check what we call the fidelity angle. So if that angle between the 2 slices is too large, so the geometry is represented 2 co-Rs, we then slice at a much smaller angle here. And what's very important, again, is that the fidelity angle is determined by the user. So there's a settings file where the user can say, OK, I want to have it this well represented, higher fidelity, less speed up, lower fidelity, more speed up. We use a similar method for the feature points on each slice. So there's a default angle we use for the zigzag. But then when we find out that there are 2 important feature points that need to be represented, we adjust the angle accordingly. And again, the feature resolution, so what is a feature point and what not, is determined by the user. So all of this goes into our conversion software. And the user just loads the 3D model, then clicks convert and exports it for the 3D printer. And again, doesn't need to know anything about the underlying conversion knowledge there. So what the software exports, it's something that's called G-code. That's the machine language the 3D printer takes. And you can see here, for instance, the G1 command tells it where to go, so gives it X, Y, Z coordinates, the travel speed, and the extrusion amount. So coming back to this comparison I made at the beginning with the low fidelity rendering, we can apply different methods from there also to our low fidelity fabrication. So you can, for instance, say this part here should be high fidelity and then the rest is low fidelity. So one thing I'm very proud of is that Wireprint got so much attention that it's now integrated into the Ultimaker 3D printer, which is the most popular 3D printer in the consumer market. So if you buy one of these printers now, you can hit the Wireprint preview, and it's going to make, for instance, one of these two objects here, which the user's already printed, not in our lab, but at home. All right, so I showed you this concept of the low fidelity fabrication. And when I did this project, I was very proud of myself. I was like, wow, 10 times faster, 40 times faster, so many more iterations you can do in a day, that's great. But if we zoom out back to the vision I showed you at the beginning, it's not enough to have this real-time physical change that enables this interactive construction. So I took a step back and I thought about how can we actually achieve this speed up, and why is it currently so limited in terms of 10 times, 40 times, but why can we not go like 100 times or 1,000 times faster? And one thing I understood is that all of the methods I used so far, they used adding or subtracting material. So each time you make a change, you actually have to add the material or like remove the material and then recreate the new geometry. So one thing I understood is that for my interactive construction approach, reshaping the material is the solution. So let's imagine this being a flat sheet, and you apply some pressure and you reshape it into this shape. So here you can see one example. So let's say we make it a sphere, and when you make it smaller, you don't have to remove the material, you just unstretch the material back into the shape. So I will tell you more about this in a minute, but I wanted to zoom out first to the second aspect, and then at the end combine the two views again. So when I started with the direct manipulation, I started out by looking at 2D. And for 2D, I used the laser cutter. So here you see one system I call constructible, and instead of using a digital 3D editor, users directly stand at the laser cutter, and they use a laser pointer to draw onto the workpiece. So I'm going to show you how I make this booklet here with the system. So here I take a laser pointer which only makes straight lines, and I draw the outline of the booklet. And as you can see, as soon as I let go, the laser cutter immediately follows and cuts. Now I take a different tool, which is called the round corner tool, and I cross off the edges. And the constructible system will make sure that all of these corners are made in the same way. Here I take the bend tool, I just draw one line in the middle, and the system will create a flexible pattern that allows me to fold this booklet. So again, the user does not need to know anything about the underlying pattern. He just needs to use these tools, and those patterns are created based on what the user has been drawing before. And at any step of this prototyping process, the user can take out the workpiece, test it, come back, put it back in the laser cutter, and continue. So the way we achieve precision is by using constraints embedded in these tools. So there's one tool for only straight lines, one tool for making the bend, one tool for making the round corners, a bit like what you know, for instance, in a Photoshop or other editing program. So we use off-the-shelf laser pointers. Middle button turns the beam on, and then we reprogram the front button to mean cutting, and the back button to mean something that we call a sketch line. So a sketch line is something like a thin line on paper. When you're not yet sure or you just want to create an alignment aid, you can hit the sketch line button. And it's going to not cut through, but just engrave a little bit into the material. And now here I'm making a box, and you can already see the base plate. And when I now extrude the side walls, they will all have the same height because they are based on this alignment aid. So from the hardware side, Constructible is based on an overhead camera which looks at the laser pointer drawing and also observes the workpiece when it's being put back in. Then we have an IR receiver which gets the laser pointer commands. We have a toolbox with tool detection based on an Arduino and some switches. And then we also query the magnetic switch on the laser cutter. So each time you open or you close the laser cutter, we can detect if you have been taking something out or put something back in. So here's a simple example how Constructible tracks and beautifies what the user has been drawing. So we use computer vision and color tracking to get the laser pointer drawing. Then we apply shape recognition with a sketch recognizer. And as you can see on the bottom right picture, we then do an alignment based on what you have been drawing previously, so everything is correctly aligned and arranged. And then at the very end of this pipeline, we also have to adjust the laser settings. So we have to set the power and the speed according to the material that is currently in the cutter. So since we have a camera in the system, we can do also other things, such as this great feature here, which is my favorite. We can also copy the shape of existing objects. So here I put in these two jars, and I take the trace tool. Just say copy, copy. And now when I take them out, the cutter will actually come and cut exactly those outlines there. So I don't have to measure, go to digital, go back to physical. I can do everything in the physical space exactly where the objects belong. So I showed you the Constructible system, but it was 2D, right? So the next question would be, how can we actually move this towards a 3D physical editing tool? And for this, I want to come back to the slide I showed you before with the reshaping of the material. So for me, the next question was, how can we actually use the laser cutter to reshape the material into a 3D object in the 2D cutting system? So here's how a laser cutter normally works. Laser beam comes out from the back. Then there are a couple of diagonal mirrors directing the beam. And then at the bottom, there's a lens which focuses the laser on the workpiece. So when the laser is focused, as you can see here, it's cutting through the material. So one idea we had is that when we defocus the laser by moving the workpiece away, we are not cutting through anymore. We just warm up the material, and then it folds down and bends into a 3D shape. So here's one example, a pen holder that the user makes. And again, just takes one tool, says bend here. And the system knows that it has to defocus the laser now, so you can see the workpiece moving down. And it also knows that for this size of a bend, it has to move the laser so and so often back and forth with a specific power and speed. So to show you one other design element we support, so it's not limited to 90 degrees bends. We can also do, for instance, a parallel suspension. So the way this works, 4 arms in the corners. And now we defocus. And now that we warm up the arms, they really unfold like an elbow. So now we move back in focus and simply cut it off. And then you can see that this was the day of the paper deadline because we use a cable to hang up the plant. All right, Just to give you a bit of an understanding of how it works internally. So the lines for cutting and bending are encoded into a 2D drawing. So red, for instance, means cutting, and then green means bending. And the number of lines simply determines the path the laser is going to take. Then this line drawing is automatically sent to the laser cutter software, which you can see here. And in the laser cutter software, different laser settings are determined for each color. So here you can see, for instance, for red, the Z-axis setting, which moves the table up and down, is 1.5 millimeters, so it's in focus. Whereas for green, it's 5 centimeters away, so then it's in defocus. So our initial version of the system used a data-driven approach. So we sampled different heat, power, and speed settings for different bands. But the current version of the system uses a closed-loop system with a thermal camera observing the temperature, because acrylic bends best at 110 degrees Celsius. So if you're interested in this line of work, we also have a second project called Laser Stacker. And for both of these projects, we have developed a calibration routine which works on your laser cutter. So if you want to give this a try, you can go to our papers, and it will tell you which settings to use for giving your laser power. So the technique I just showed you pushed a bit more towards 3D, but as you saw, it was limited to origami-like geometry. So the question is, how can we make this really 3D? And for this, we looked back at what did the laser origami characterize. So the path was with a 2-axis motion table. Then heat came from a laser. And then the pressure was determined by gravity pushing the workpiece down with its own weight. So to give this more degrees of freedom, we built a system based on a 6-axis robotic arm. Heat comes now from a heat gun. And the force comes from a compressor pumping air into the workpiece. So here you see a user, and she indicates she wants to have this circle here warmed up and reshaped. Now we warm up the area, and you can see how the material becomes compliant. Now she can actually go in there and pull the material out. So at the beginning, I showed you this vision of hands-on editing, kind of pushing and pulling on the material. And with this more formative fabrication approach, we get very close to it. So users can work hands-on on the material. They pull it out, push it out, and they receive immediate physical change based on what they are doing. So as you can see by the simple shape we are showing here, this is currently work in progress. So there are a lot of optimizations we can still do. So one is, for instance, you saw that the heating still takes a while. But we think we can actually get to a transition within just a couple of seconds. So the way we want to do this is currently the material is at room temperature. So it takes a while to actually get it to the point to make it compliant. But if you preheat the air within the workpiece, just below the transition point, we can make the transition with just a few seconds. And then also the shapes are currently very simple because we only have one size of heating mechanism. So once we are close to this transition points, we want to use an infrared LED array where you can actually individually address the different LEDs, turning them on at different heats. So behind the scene is this software system here. So we run a physical simulation of what we are going to accomplish in terms of shape, then instruct the robo arm to move a certain path with the heat gun at a certain temperature, and also have to turn on the compressor to pump the air in at a certain rate. However, as with any system that involves some real-world aspect, the simulation is never perfectly precise. So we also measure with a distance sensor and a heat sensor how the material is actually developing and feed this back into our physical simulation. All right, so I showed you at the beginning my vision of interactive construction. And I believe that when we can make these shapes more complex, we get very close to this pulling, pushing system. Also with the compressor pumping positive air, we can also have negative air, so we can also pull parts back in. And with this, I want to move towards more where this is going in the future. So I showed you at the beginning my very long-term goal that I want to allow everybody to create complex physical objects. So I showed you this new interaction model of physical editing directly in the space. But the next question on top of this is really, how can we allow people to create more complex objects? Because all of the objects you have seen so far were pretty simple. So how can we create objects that require advanced domain knowledge that the user normally does not have? So one insight I gained is that users are really bad in designing from scratch. So it's kind of this white paper phenomenon. People don't know where to start from. So I believe that the future of fabrication will actually lay into the remixing of existing designs. So the problem today is that, yes, there are these 3D model databases, but you cannot remix any of these models because they are plain triangle meshes. So there's no metadata attached. So to enable this remixing of the physical designs, I therefore want to create an ecosystem of reusable parts. So as you can imagine, if you remix 2 digital designs, it's already very difficult. But if you remix 2 physical designs, also mechanical properties play a role and material properties. So just take a chair and you want to add a leg to this chair from a different design. This leg now needs to know how to reshape itself to support a certain weight. Same thing if you change the material of that leg, it will also change how the geometry needs to support that weight now. So there are several ways how we can actually create this metadata for this physical remixing. So we could, for instance, ask the designer of the part to annotate the part explicitly during 3D modeling. But then the question is, the benefit actually lies with the end user of the part and not with the creator. So how can we motivate the creator to create this data? Another option would be to implicitly reason from the tools that the designer is using, what's the purpose of that part? And finally, we could also use, for instance, one annotated 3D model to reason about the function of other parts in similar 3D models. So we could also ask the user to use existing physical sources, so for instance, to 3D scan a part in his environment, take a photo or a video of a function by example that he wants to reuse in his design. So in addition, the question remains, should it be all humans generating this metadata? Should it be all algorithms, or is there a solution in the middle? So for instance, given the current efforts in like crowd design and expert design, are we going to have a tool integrated that allows me to query certain experts for subtasks in my design goal? Especially with physical designs, we also have to think about different output devices. So one user might have a 3D printer that is very high resolution, multi-material. Another user might have a 3D printer which has only one material and is low resolution. How does a design know how to convert for these different output devices? And finally, the question remains, how are users actually going to remix existing designs? What's the interaction model behind? What information will they need to remix these designs? And I will tackle this as my first research question because it will determine all of the above layers, which information we actually need. And the last aspect I just wanted to note is that when we talk about physical design, we always talk about a range of different properties. So at the easy level, it's about shape and color. At the more complex level, it's about sensing the user, so interactivity, reacting to the user input, or even having mechanical functions included there which require kinematics or knowledge about dynamics. And at a very high level, we can also start thinking about, for instance, sustainability and intellectual property. So what does it mean when everybody can create physical objects very easily? Physical objects require material, they create waste. Can we design with reusable parts? Or can we have a physical undo, for instance? So with this, I want to end my talk, and I just want to take a minute to thank my advisor, Patrick Bordish, and all the students who work with me, either on research projects, so they co-author my papers, or especially the undergrads, they help putting my software open source or pushing them out into the 3D printing devices. So thank you very much, and I'm happy to take questions.
you're building things with software, you can change your mind over and over again and do something and undo it and do it and undo it and so forth. With these materials, is there a memory where you can't do that too many times or it degrades?
So for me, the question boils down to, is there a physical undo? And that's one of the big open research questions that's still there. So I would love to collaborate, for instance, with a material scientist to look at like different materials that would support this. So for instance, for the material we currently use for the stretching, if you stretch it too much, there's no way to flatten it out again. But there might be a material which allows for these properties, or a material that can be engineered for this purpose. So for me, that's an open research question for like next research years. Yeah. Do I moderate the question?
Sure, go for it.
Have you or others looked at what a software person might call interactive debugging? You know, I ask it to print something and print it exactly what I wanted, but the physics are just wrong. It falls over, it breaks, and I want to be able to explore why in an effective fashion.
Yeah, it's a good question. Oh, and I should repeat the question for the recording, it just comes to my mind. So the question was, is there like support that helps you with, for instance, mechanical properties or like physical law properties like falling over or breaking? Definitely a good point. This is the next step in terms of research to support the user in this, because users are really great in modeling shape, but they are really bad in thinking about like forces, because forces are invisible. People have no understanding of what is involved. So for instance, when you, especially what you said, when you create a physical design, it might fall over because the center of mass is somewhere else. So the user needs to get some correction, and then the question is, how does the interaction look like? Will it automatically be corrected, but then the user might be surprised about the output? Or should the user be informed and then make a decision in how much he wants to change his design? Yeah.
So I guess the opposite side of undo is preview, right? And some of the techniques you're doing, until you've seen it the first time, you wouldn't expect that it was even possible, I guess. And so I wonder if you've thought about how you can show what's going to happen before you consume the material and things like that.
Yeah, for me, this again comes down to the question, is there a physical undo and is there instant fabrication? Because if you have these two, there's no reason why you would want to have a preview. So I think right now I would totally agree that, for instance, if I would commercialize the constructible system, I would put a projector showing you where things are and going along the path before you actually cut it. But with a long-term vision in mind, I think like if you have adding and subtracting or some reversible formative fabrication process, this would not be necessary anymore. So another answer to or aspect to that question is also, what is like the benefit of AR versus physical construction? And I think AR is really great if you want to display something, right? If you want to just show the shape of something in some context, but it's not good if you have to test the function of an object. You can display a bookshelf, but you cannot test if all your books fit in there, right? Then you need the actual physical version. And it's the same with the glasses. You can display the glasses, but how it feels is something you can only test with the physical version.
Okay, let's thank Stefanie one more time.